quite a good group of people, so it's really my pleasure today to host this webinar in the GEO AI4EO series. So I am Andrea Scetti, I work at KTH, and we are working within this group to promote more seminar in this intersection between AI and EO and also Earth observation data. And it's a pleasure to see that Frank is here for presenting us this interesting work. And also I saw now Professor Keshav. Yes, yes, hello, hi.
Hello.
Nice to see you. So yeah, we're just starting. So
thank you.
So yeah, it's a great pleasure. So we can dig into this new foundational model that is called TESSERA, developed by the Cambridge group, led by the professor Srinivasan Keshav, that is a professor of computer science at University of Cambridge, and Feng, that is one of the contributor of this great work. So we are looking forward to dig into your foundational model and the interesting application also that you will show us. So I think you can start as soon as you are ready to share the presentation.
Yes, so I think I'm going to share my window. Give me a sec. Okay, cool. Can everyone see this? See my window? Okay, cool. So yeah, without further ado, let's just get started. So yeah, I am Frank. That is my English name. So my Chinese name is ZhengPeng, and I'm from Cambridge. I'm a second-year PhD student, and today, I'm very honored to present my work to Sarah here, which is one of my actually this is my first like PhD project. So yeah, just without further ado, let's just get started. So TESSERA, this is an acronym. So it stands for Temporal Embeddings of Surface. Temporal embeddings of surface spectra for Earth representation and analysis. So in short, TESSERA. And also, although I'm the first author of this work, but it is I've been collaborating with other group members as well. So with Professor Clement and also with Keshav, with Anil, and also with other like amazing colleagues. So this is not done by my own, and this is a very collaborative work. So yeah. Okay, so yeah. So for the introduction, like why observing the Earth, right? So we know that like this is super important. We get to monitor the land use. We can access the status of the crop, the field, the forests, and also we can quantify the forest degradation, carbon stock, and etc. So it's super important to observe the Earth. And right now, I think one major way that we observe the Earth is using the satellite images. And so at the moment, we got like lots of public like satellite data, right? We like every day we got petabytes of like new satellite data generated every day. And so, but there are some challenges with this images. So let's talk about like so I think this is Sentinel-2 images. So for Sentinel-2 images, I think one challenge that we have is the cloud issue, right? And also you can see the GIF I showed here. We also have this like changes in lighting, and also we've got like varying time gaps because sometimes it only takes like 6 or 9 days to get another image, but sometimes it will take longer. And also we've got Sentinel-2, we also got Sentinel-1, we also got Landsat, so we got like a variety of sensors. And another thing, so right now to tackle all these issues, so one of the it's not the common practice, but one of the practice we're using is the so-called temporal compositing, where we just somehow mosaic all the images together to form a cloud-free like image. That is one of the practices. But the thing is, by doing this, we're going to lose the temporal signal, which is super important in many downstream tasks. So here I just put some examples here. So let's say if we want to identify different like tree species, we can identify by their like temporal signal, as well as the image I showed here on the right side. So we know that like seasonal dynamics help to identify land cover and also detect the changes. So temporal signal is super important. So let's just take a look at right now the common paradigm from satellite images to the insights. So this is the image brought from Google Alpha Earth. So yeah, image credit to Alpha Earth team. So here, so from raw satellite images, we've got, like I mentioned before, we got like different like sensor types. We got star data, we got optical, and also other like satellite images. So here we need to go through some pre-processing processes, and then we're gonna like extract the features. Then we do some like further modeling and analysis. Then finally we can get some insights. So this is like a typical like paradigm for people to analyze the remote sensing like imagery. And yeah, so here I just draw a bounding box. I think I would just sorry, enable a laser here. So yeah, um, so here let's just draw a bounding box of this part. So we know that this part is super important, right? Especially when it comes to feature extraction, because we need to extract some useful features from these satellite images. So if we just draw a bounding box here, then this is how the current like remote sensing foundation model does. So basically, remote sensing foundation model can help you with all this like bounding all this like components in the bounding box. And right now here, this is just a taxonomy of the current remote sensing foundation models. And you can see there are at least like 200 of them out there. So we've got a variety of like remote sensing foundation models. We go like like I think I just listed some of the here, like Scale MAE, SATA MAE, and also Chroma, DOFA, and also Alpha Earth, and also TESSERA is actually another like remote sensing foundation model. So yeah, we've got a lot of like varieties and also a lot of choices here. And also here, this is like the paradigm for TESSERA. So what we did is like we have this raw satellite images, and then we input into the geo foundation model. Like here, this is TESSERA, and then. But I think what distinguishes TESSERA from maybe a lot of other foundation models is that we can generate this like the so-called 128 dimension representations for each 10 by 10 pixels. So here, this is quite different from any other foundation models, because as far as we know, like for many other foundation models, they don't really provide this like embeddings. So for them, it's more like an end-to-end fine-tuning or training. So they didn't really like output like this intermediate like embeddings. So I think this is quite important. And for those of you who might not have heard a lot about like representation or embedding, so here in my talk, I think embedding and representation, they are the same thing in this context. So embedding is essentially like just some numbers, and these numbers contain some like hidden features of the pixel. So yeah, this is the easiest way to understand these embeddings. So for TESSERA, what we did is like we input the raw satellite images into the TESSERA model, and then we output the embeddings. Then we just use embeddings for further modeling, analysis, and then we got insights. So yeah, so that means if you just take a look at this figure, so for TESSERA, we actually like users don't need to deal with the raw satellite images. So right now we just provide this like 128 dimension representation or embedding, and then the users can just use the embeddings for their downstream tasks. So I think this is like the major difference between TESSERA and also a lot of other foundation models. And yeah, so I think before diving into our methodology, I would just briefly introduce self-supervised learning, because I know like maybe some of you might never use that, because I know like in remote sensing, most people they use supervised learning, and they use so here I would just talk a little bit about a very classical like self-supervised learning algorithm. It's called masked auto encoding. And so what we did is like, let's say we got image here. What we did is like we mask, let's say 80% of the pixels, and then we input this, then we input this image into encoder, then we got the representation, then we attach a decoder to reconstruct the image. Then, so for training, we can just simply by answering like, are these images similar? If they're not, then we just somehow, penalize the model. And then, so finally, we can get something like that. So this is like a very, very typical self-supervised learning algorithms. And then if the training goes pretty well, like you see, like the image pair down here, then we can basically just get the encoder that we know that this encoder is pretty, I think it's pretty powerful to extract the image features. Then we can just take this encoder out and then use it for whether fine tuning or like future learning, whatever. So yeah, this is like a very, very typical way for like self-supervised learning paradigm. But TESSERA is quite different. So we're still using self-supervised learning, but we're not essentially using like masked autoencoder or so what we do, so what we use is an algorithm. It's called battle twins. So let's just take a look at the image up here. So in the right upper corner. So let's say if we just shoot a laser to this like series of images, and let's say for each of these images, they are like multispectral imaging, and what we can get is a data type that we use that we call it as D pixel. So essentially, for a D pixel, it has two dimensions. One is spectral, and the other one is the observation dates. And we know that for Sentinel-2, for example, for Sentinel-2, we got some clouds there. So obviously on the y-axis, there are some missing values because these values, they are invalid. They are like corrupted by clouds. So what we did is like, and also here as an example, let's say this pixel is a cone. So that's why we call it like cone D pixel. Oh, sorry, cone pixel. Let's say this pixel is a cone. Then what we do for battle twins is like we sample we did like two augmentations for this D pixel. So for the first branch, what we do is like, since we've got like a lot of like observations, right? So let's say we just sample 20 of this observations, and then this will give us the first branch or the first augmentation of the cone. That then we call it a cone with distortion. Here with distortion means like we only select 20 time steps out of it. So we're not selecting all of them. So basically this is a distortion, right? So this is only like a fraction of this cone like pixel. Then for the second branch, we're doing the same thing. Like we sample it and we got the second cone with distortion. And what we did is like we input these two augmentations or two distortions into encoder and got the representation, and then input them into a projector to get a larger embedding. Then we just calculate the loss between these two embeddings. And here I didn't list like the how to calculate loss because this would not be the key point of this talk. But I think here what we want to know, what we have to bear in mind is that essentially, although there are like two coins with distortions, but essentially they're the same. They're just coin, right? So here we just minimize their like we just like reduce the redundancy of these two distortions and to keep only the most essential part of the information. So by doing this, we just train a model that can learn like, okay, that can extract the most essential information from the pixel. So this is how we train the TESSERA. And yes, and also here I just show you, this is like the whole pipeline of the TESSERA. So essentially we have two like modalities. The first one, we have the Sentinel-2 branch that we just extract the D pixel and we do the sampling input into encoder one, because this encoder one is specific to process like Sentinel-2 images. And also we have the same branch, another branch, which is responsible for processing Sentinel-1 images, doing the same thing. And here, what's different is here. So here we have MLP to fuse their like features, then input into the projector and doing then try to like I mentioned before, we have this loss function. We try to reduce the redundancy, only keeping the essential information. So this is like the whole pipeline of training the TESSERA model. And yeah, so this is just like a summary. So what TESSERA provide is like we have this ready to use representations, and right now we choose the dimension of the representation to 128. This is like the trade-off, because like we find that like 128 actually like can contain a lot of information while doesn't really need a lot of like space to store them. So 128 is like the trade-off. And the other one is that we know that we actually encode the temporal spectral temporal spectral signal. So we know that like these embeddings contain like very rich temporal spectral signal. Also, we're doing a sensor fusion. We did it for Sentinel-1 and also for Sentinel-2. And our aim is to provide this like global like embeddings for everywhere on Earth, and also at 10-meter resolution. And also our model is open, it's fully open source. So you can find our training script, inference script, and also yeah, you can just reproduce our results and all the code is on our GitHub repo. Okay, so I think I just talk a lot about the methodology. I think here, this is my favorite part actually. So this is like the visualization of this embeddings. And like I mentioned before, we have 128 dimension embeddings. So here I just choose the first 3 channels. And here, these are like very colorful RGB images. And yeah, here I just show you like 6 different places, but actually I have more images later that I'll show you later. Okay, so yeah, so here I actually just added this slide because I know like Alpha Earth is like the elephant in the room. So here I have to mention that. So here, this is just a very rough comparison between Alpha Earth and TESSERA. So this is like this is a crop field from near Vienna. And what I want to emphasize is that since Alpha Earth is doing it in a patch-based way, while TESSERA is a totally pixel-based method. So you can see so you can find this like square-like artifacts in the Alpha Earth embedding, while you don't really see this in the TESSERA embedding. So this is like a visual comparison. But I will show you more quantitative like results later. And also here, this is also a rough comparison between TESSERA and Alpha Earth. So for TESSERA, we only use Sentinel-1, Sentinel-2. This is like we only have these 2 data sources for training and for inference. But for Alpha Earth, I think they've got a lot of data. So I think Sentinel-1, Sentinel-2, and Landsat are their inputs, but also they use text and I think JEDI, like other data sources as their training objective. So they've got like a variety of data sources in their pipeline. And also for coverage, I mean, right now, Alpha Earth, obviously they have already like achieved the global coverage from 2017 to 24. Right now, we're still trying really, really hard towards this aim. And for embedding dimensions, it's also quite different. So for us, we use 120 dimension, but our embedding is quantized to integer 8. And so for Alpha Earth, it's 64. I think they use flow 64. And yes, so we're both annual like embedding, and we are both at 10-meter resolution, and the method is quite different. Like I mentioned before, Alpha Earth is patch-based foundation model, while TESSERA is just pixel-wise. And so for open source, we're just fully open source. And since for Alpha Earth, I don't think they have open source their model. So what they can provide is their embeddings, but they don't really provide their model. And also we have different licenses. And yeah, so this is just a rough comparison between Alpha Earth and TESSERA. Okay, so let's just I think this part is quite important. So like how well does this embeddings work, right? So what is the quality of this embeddings? And we did a range of evaluations. So the first task we did is a crop classification, and this is the data set that we're using. So this is from Austrian crop. This is actually open sourced, but we further like process this data, and also this data will be also open sourced. And so here I just have a table here. So what I want to emphasize is that this data set is a little bit unbalanced. You can see like wintergreen takes up like 1/3 of the total number of samples, while if you see here some like other plants and also grapes and tree fruits, they're like underrepresented in this data set. So in summary, this data set is a little bit unbalanced, and that's why it's a very challenging data set if you want to do like crop classification or like segmentation. And here are some results. So we use this data set for 2 purposes. So first one, we can use this data set for classification. And here we only evaluated, I think, 5 different scenarios. So first we have TESSERA, and then this like reddish and also this orange lines. These are the baselines. So that means we're using the raw sentinel 1, sentinel 2 images, and together with the random forest or with the MLP. And then Presto. So Presto is another pixel like wise foundation model, and also GSE. So GSE is essentially Alpha Earth, because I think before like Google released their archive, I think the name of the of this embeddings are called Google Satellite Embeddings, but then they changed the name to Alpha Earth. So here we still use like GSE here. So basically this is a result like show you. So the y-axis are the weighted F1 score or the macro F1 score, and the x-axis, this is the total label used. So if this is like 0.01, that means we only use like 0.01% of labels for training, and then for like 0.3, that means we're using like 30% of labels for training. So here we just want to demonstrate the label efficiency of TESSERA in this specific like downstream task. You can see if you only use like 1% of data for training, you still get a pretty high F1 score. And here, so for figure C here, so the y-axis is still weighted F1 score, and the x-axis is the samples per pixel. So this is like a more challenging like test that we did. So here, if the sample per pixel is 1, that means I think we have 17 classes in that data set. So that means we only use 17 samples for training, and we repeat this test for 2,000 times. And this is like the confidence, the error bar that we get, and also the like the mean value we get. And here you can see this is just we're just trying to simulating the like the extreme case where we have very few labels. But you can see like TESSERA still performs pretty good. Like when the labels when like samples per class is only 10, that means we only have 170 like samples for training. We still get a pretty high like weighted F1 score. And yeah, so this is one way that we can use, one way we use for like this Austrian crop data set. The other one we can do is like we can do patch-wise segmentation. This is like very like typical CV task, right? So this is the Austrian crop region, and it's a very very simple like data split where the lower, I think 60% are training, and then the other 2 regions there for validation and also for testing. And these like patches, they are 64 by 64 patches. So here are some results. And also we have to say here we use the Pangea framework for evaluating. So basically we just incorporate this like Austrian crop dataset into the Pangea framework, which is super helpful. It saves like a huge amount of time when doing this like. And also we added Galileo like model and also the SkySense model into the Pangea framework. And these are the results that we got. So here, these are the different types of model. And here 1% means we only use 1% of data for training. 100 means we use all the data, all the like training samples for training. And these are the results that we have. So you can see TESSERA performs pretty good on this like patch-wise segmentation on the Austrian crop data set. And yeah, and also we did other like test sets as well. So this is projecting the forest height where we have this embedding. So we just you can just perceive the embeddings as like as an image. It's just like this image is not like typical RGB image. It has 128 dimensions. It has 128 channels. So what we did is like we input this image into a unit, and then we can just use this unit to map from the embeddings to the ground truth like canopy height value. And these are the results we have. So TESSERA can achieve like over 0.6 in this like so by the way, so this is the ground truth data that we have for Borneo. It's a place in Malaysia. And yeah, so this is another downstream task that we did. And also we compare TESSERA's performance against other like products or other foundation models as well. So for Presto is doing pretty good as well. So Presto can do like 0.5 on R square, and also the RMCU looks overall good. And Alpha Earth is a little bit worse, at least on this data set. It's slightly worse than Presto, and also with so this composite is like the baseline. Let's say we just use the the Sentinel-1, Sentinel-2 composite as the baseline. And then here, so the second row, this is other like global model that we evaluated. I mean, this obviously this global like models will perform pretty bad on this like regional data set. So this is expected. All right, so here another like task that we did is this is like the wildfires in California. So basically, we just want to detect like the fire severity in like California. Here we only did it for 2 patches, but actually we're gonna have we actually right now doing like more, but I didn't put the results here. So figure 8, this is super interesting. So what we did is like we reduce the dimension of the 128 dimensions to 2 dimensions and using the UMAP. And you can see here, this is a very clear delineation of the like unburned region and also the June fire and the August fire. And also, if you just take a closer look at the August fire, there is a clear gradient showing the fire severity from like low to moderate to high. So that means like these embeddings contain very good temporal information, right? And also for figure B, this is just a comparison between TESSERA and also this is the task-specific composite. This is like the baseline, and also GSE stands for alpha Earth. So in this case, alpha Earth doesn't like perform really good on this like data set. So yeah, and also TESSERA performs slightly better than the baseline, where we're only using like the Sentinel-2, Sentinel-1 composite. And here, figure C, this is just showing the ground truth versus the prediction. And also we can achieve actually very high like F1 score. And yeah, so also this is just like another downstream task that we did. So this is biomasters. This is also incorporated into the Panja framework, which we really appreciate, because so what we did is like we compare TESSERA against the Alpha Earth, and also this is Spectra GPT. This is another foundation model, and we only compare against TESSERA against Spectra GPT here, because Spectra GPT is actually the best foundation models in other foundation models categories. So we only select the Spectra GPT here. But you can see in terms of like RMSE and also R square and also other metrics. So still TESSERA performs slightly better than Google Alpha Earth. And so figures that this is the ground truth versus the predicted. And I mean, at least visually, it looks really accurate. And yeah, and also this is like another small project that I did just for fun. I didn't put it into the paper, but it's just for fun. So here on the left, this is the embeddings for Cambridge, and on the right, this is for London. And here just make this animation showing the embedding like from 2017 to 2024, and you can see how it changes across time. And also what I did further is that actually you can just calculate the cosine similarity between the 2 adjacent years of embedding. Then you can set up a threshold and you can tell like which places have been changed, right? So this is just a very simple idea. But I mean, yeah, this is how it looks like. So from 2017 to 2017 to 2019, and then to 2024. This is how Cambridge has been changed through the past years. But yeah, this is just for, yeah. So that means like we can also use like TESSERA embeddings for this like annual land change detection. And here I also did other downstream tasks. So I use like TreeSet AI. This is another benchmark data set that I use the Panja framework. Actually, I incorporate this data set into the Panja framework work as well. And here I did it for, all these like other foundation models, and TESSERA performs the best. And also for Austrian crop, like I mentioned before, it is really good. And for pastis, actually like Alpha Earth also does very good on pastis data set. I mean, it's even better, slightly better than TESSERA. But yeah, Alpha Earth is doing good on pastis. And also for biomasters, TESSERA is good, Alpha Earth is not bad. And also for Borneo, like the canopy height task that I mentioned. So yeah, this is like the radar pool showing the capability of TESSERA and also other foundation models. All right, so I think I just talk a little bit about some like system as aspects, because I think I don't know if you can imagine that this is actually a very, very data intensive task, because our aim is to publish the global embeddings for every pixel on Earth. So this is super, super data intensive. And basically, this is a rough calculation. So we're going to need 1.6 million GPU hours together with 11 million CPU hours to process all the to process the embeddings from 2017 to 2024. And also here, these are the computes that we're using at the moment. So we are supported by the Dawn computer. This is a supercomputer in Cambridge, and we got access to 24 nodes of this like very powerful like supercomputer. And also we have support from AMD as well. And also we've got some like local machines here, also some like other tiny like toy machines as well. Yeah, and also to because also like I mentioned before, we're gonna pre-compute all the embeddings, and we're gonna publish all the embeddings. So we're gonna need about 3 petabytes of the storage to host all this like 8 years embeddings. And also one thing I want to mention is that right now we're still super, super CPU and GPU hungry. So if you want to collaborate, if you have some like ideas that if there's a way that we can collaborate, just feel free to reach reach out, whether me or Keshav. Yeah. And also here, I just want to talk a little bit about the TESSERA toolkit, because this is super important. This is our greatest contribution to the community, right? So for TESSERA, we have, like I mentioned before, this is a fully open source model. So this is like the main repo of TESSERA, where we have all the training code, all the inference code. So you can just use this repo to create embeddings yourself if you don't want to like use the pre-computed embedding, if you want to like know what are all the ins and outs of these embeddings. You can just create the embeddings yourself. And the second one, this is actually the most important one. So we have this GEO TESSERA library. This is a Python package that we use to release all this pre-computed embeddings. So here, this is a map showing the data coverage. So right now, we still haven't fully achieved the like global coverage because of compute, but this is just a matter of time. And so right now we're prioritizing the embeddings for 2024. But if the users they want to have like other years of embeddings, they can actually just open the issue under our GEO TESSERA repo, and we're gonna just prioritize their request if their request is reasonable. And so the third one is the interactive like tool that we developed. So basically, this is just a Jupyter notebook. They can just select your region of interest, and then it will just automatically load the embeddings for that region, and then you can just like add some labels. Let's say if these are the water, these are like crop field, then you can just click classify, and it will just show you the results, which is super, super cool. But this is not done by me. So this is done by one of my amazing like teammates, Robin. But yeah, I don't think Robin is here. But yeah, okay. And also here, this is like the uh this is basically a flow chart of the TESSERA, like sorry, GEO TESSERA, like how to use this GEO TESSERA. So basically, the user can just input a bounding box, like basically just determine like which areas of embedding you want. Then the program just will send a request from the GEO TESSERA library. Then GEO TESSERA library will just pick the areas. Then we just return this embeddings, and then this way the users can just get this TESSERA embeddings. So the shape of the embeddings will be H by W by C. Like I mentioned before, you can just perceive as an image. It's just like this image is super, super like chunky. It has like 128 dimensions. Then once you have this image, you can just input into a very, very simple like model, because like I mentioned before, these embeddings, they have like very rich semantic information. So you can just input into a very simple model like MLP random forest. Then you can just apply it to various downstream tasks, classification, segmentation, regression, and yeah. So yeah. And also here I want to like talk a little bit about a small project that I did, which is super, super interesting. So I think 2 weeks ago, I just want to track all the farm like farm PV panels in the UK. And actually, I just did this in 2 hours, and I can just show you like how I did this. So basically, it takes me like 1 minute to just check the data of availability map in the GEO TESSERA repo, because we prioritize the embedding generation for the whole UK. So you can see like the whole UK region is green. That means we have the 8 year of embedding, which is cool. That means like I can do this. And then it takes me like 1 hour to download all the embeddings for the UK from 2017 to 2024. Then I just hand like created some of this like PV panel labels. So I think this is just a place near London, just a random place near London. And it takes me like 15 minutes to create some like to create some like PV labels. Then I just ask Cloud Code to give me a like pipeline for pixel-wise PV like panel detection, and Cloud Code does a really good job. It can finish this in within like 10 minutes, and then just train the XGBoost model. It's actually pretty fast because I've got very few labels, right? I think just like nearly 50 polygons. So it's a very like a small number of labels, and just take me 1 minute to train the model, and then I just use this trained model to detect all the PV panels in the UK from 2020, from 2017 to 2024, and the inference takes a little bit longer. It takes like me like 40 minutes, because you can, although UK is relatively small, but still we have like 80-year data, so it takes me 40 minutes. So in total, it only takes me like less than 2 hours. So this is like the pipeline of a downstream task. And here are some results. So I think the question is like, does this result look good? Because it seems like a very like uh, very coarse like pipeline. So actually, it performs pretty good. So if you just take a look at the right on the left side, this is a global data set. So yeah, I think to generate this data set, they use some like Sentinel-2 images, and together with the CAN to detect, to segment all this like PV farms. And on the right side, this is TESSERA. So you can see we can actually capture more this like true positives here. Like I highlight them using the circle. And also one thing to mention that is that, so the above two outputs are actually from the year of 2020, But actually we use like 2024 embeddings labels for training. So we're not using any data from 2020. So that means like these embeddings have very good transferability across time. And also here, this is a very interesting demo. Like, so this is a place, I think this is a place in Scotland. And so this is from 2017 to 2024, and these are the prediction results. And you can see in 2024, there are clearly like more PV tasks like pop up. So I just checked the Google Maps, and actually this is true, because in 2023, basically this is a farmland, and 2024, there are more PV panels installed. So that means like this very small model can detect PV panels very accurately. And also this is a place in Scotland, but actually the training data is only from a place near London. So that means like this model or these embeddings have also very good like transferability across like different locations. Yeah. And yeah, so finally, this is our team. So we're a highly interdisciplinary team. We have people for computer science, which I'm one of the members here, and also remote sensing. And also I know a little bit about remote sensing, and also we have people for agriculture and ecology as well. And yeah, so this is basically the last slide of my presentation. And like I mentioned before, like right now we're looking for collaborators. And if you're interested, you can just scan the QR code to read our paper. And also we have all the data, all the code checked in our GitHub repo. And I think we still have some time for questions. So if you have any questions, just feel free to ask.
Okay, thank you, Frank, for the nice and clear presentation. We already got like plenty of questions in the chat. I'm not sure that we'll have the time to reply to all of them, but for sure to some of them. Let's get started. Let's see. I also saw that Keshav already replied to some of them. Thank you in the chat. So maybe we can start with some live questions. I think Isaac wants to ask a question. Then I will pick up one from the chat.
Yes, hi. Can you hear me?
Yes, I can hear you.
Yes. Thank you very much for the presentation. It was great, like really clear. You touched upon the transferability across time here in the last downstream task. I was interested, like, have you tested, like, what perform? I have two questions basically. What performance can we expect on tasks that involve years that you have not trained the Tessera model on? So like 2025, for example. And the reason I'm asking is because one of our use cases would probably be that in like maybe July, we would like to produce embeddings. Like, or for example, 2026, when we in July, we only have satellite data up to that point, but then we can basically just mask the rest of the year to Tessera, I guess, and pretend that they're clouds or something like that. What performance can we expect for the embed? We can train embeddings to predict the crop type for this year that Tessera wasn't trained on. Is that clear?
Yeah, I think that's pretty clear. So the first question is like, so right now, yeah, like we trained the TESSERA model on data from 2017 to 2024, and we know like I think we're about to have the 2025 like the whole year data. So yes, and TESSERA is not trained on that. So for this question, we haven't really like evaluated on that, but I think there is a thing that I want to mention is that so in our previous work, this is done by Professor Clement. So I think in their test, what they did is like they only trained the model. They only trained the model using data, I think, after 2020. But they found that actually these embeddings, or at least this model, can generalize pretty well before the year of 2020. So they use the model, same model, to generate the embeddings for 2017 to 2018, and they still find that the result look pretty good. I think so. I think probably this will be the same thing for Tessera. So I'm not super worried about that. And the second thing that you mentioned is that let's say right now we're in like October, right? So that means we don't have the data from November and December. So yeah, so that means like if we want to create the whole year time window, let's say from January to December, then we're gonna have 2 months of missing data. So I think in this case, what we can do is like we still maintain this 1 year frame, a 1 year time frame, but we can actually fill in this time frame using data from October 2024 to October 2025. So in this case, the time frame will still be 1 year. It's just that we use some data from the previous year. But I think in this case, it's still valid to do so.
Okay, thank you very much.
Yeah, thank you.
Thank you. Thank you for the question. I think following a bit of trying to summarize the question here in the chat, there were several questions regarding the possibility to use also Tessera not for annual embeddings, but for monthly or some other ask weekly and representation. So what is your like suggestion here, Frank and Keshav, and what are maybe the next steps also that we can imagine for this task that are demanding more
Yeah, I think the challenges of like producing the weekly or like even daily embeddings, I think the challenge is it's just like let's say for weekly. So basically for Sensor 1, Sensor 2, we cannot assure that every week we have the data. So I think in this case, I'm not quite sure if weekly embedding is doable and also it's worth doing. I think but I think definitely for, let's say, for seasonal embedding, let's say we have embedding for spring, for summer, for autumn, this is totally doable because I can imagine that within a 3 month time frame, we still have maybe like 5 to 10 or maybe fewer satellite observations within this time frame. But if this is too fine grained, let's say like daily or weekly, then my only concern is that we don't have the raw data to generate these embeddings. So yeah, but I think in terms of like seasonal like update, I think this is totally doable, and this is definitely something that we want to have in future work.
Maybe I can jump in here
Yeah.
briefly. So I think I've answered quite a few questions in the chat while Frank was giving the talk. And I think this question of sub-annual embeddings comes up many times. One issue is the compute time. Even for doing 1 year is quite challenging. And I think that's one problem we run into. So doing sub-annual means we have more embeddings. If you do every quarter, for example, you need, 1 petabyte of storage per year. which is significant. The second issue is that, let's say you have a crop and, the pixel that's being observed is going to be brown earth and then green crop and then it'll grow and then it'll be harvested. That's a signal that's annual. If you do sub-annual, you only get parts of it rather than the whole thing. And so we believe, at least I believe, that this particular encoding of the complete cycle in the annual time scale is what makes the embeddings good. So sub-annual embeddings will probably lose that signal, which is why, I mean, in any case, we don't have the resources to do it, but we believe that annual is the right time scale. Nevertheless, we would like to detect changes faster than annually, but that's a different problem than having sub-annual embeddings.
Thank you for the remark. I think yes, we understand the goal of having annual embeddings and the difficulties and maybe the challenges of going monthly or seasonal. Maybe I think there was also about a question about the reason why TESSERA is performing so well. And I like your answer. I mean, Keshav, that in some way your model is simpler if we try to like summarize it very quickly. And I think that was a very interesting point that you show that maybe with a less parameter we can still achieve quite interesting results. I don't know if you want to comment on it, maybe live in the discussion.
Maybe I can do this. This is actually an insight due to Clement. I've been working with him for the last 3 years, and he's very, very clear on this, that pixel-based embeddings are very important for two reasons. One is that they don't get corrupted due to boundary effects, especially like field effects or edges of roads or in urban areas. Because the boundary would be, let's say if you have a 3x3 patch, you're talking about 30 meters. Whereas if you have a pixel, it's 10 meters. So we do all the patch-based approaches in the downstream task. For example, Frank showed the UNet, which is a patch-based for canopy height estimation. The other thing is that, the Google Foundation model, we were quite worried about it. And then we realized that, it's not performing that well, probably because we suspect it's because it has so many things in it. It has 10 or so different target downstream for the lost target task for downstream whose weights are unspecified. And somehow keeping it simple seems to make a difference.
Yeah, it's very interesting. Thank you for the remark. Let's see, any other question, maybe live questions, if someone has some other questions in the audience. No, some of the questions were like also some more technical details. I guess you already replied, Keshav, and they can always find it in all the documentation that you share with us. Maybe I will have another question. Are you planning for future work also to go behind Sentinel-1 and Sentinel-2 as input modality for the foundational model? Now you focus on Sentinel-1 and Sentinel-2, and it was, in my opinion, was a very wise choice. I mean, this is one of the most used archive in free remote sensing, let's say, free imagery. But what is your maybe interesting next step if you want to share?
Yes, so I think I was just gonna talk a little bit about this. So I think the next step, I mean, we have a lot of like future works. I think I talked to Keshav a lot about this. And one future direction would be incorporating more modalities. Like we're considering doing for Landsat, because we know that Landsat has available data since 1972. I mean, if there is a way to somehow align the Landsat embeddings or maybe the Sentinel-1, Sentinel-2 embedding, probably we can just like farm out the embeddings from current to 1972. So that means like from 1972 to right now, we have annual embedding for Landsat. I mean, that is one of the idea that we can. But right now, I think what I'm focusing on is that right now I'm developing a real-time change detection model based on TESSERA embedding. So what we want to do is that we want to do near real-time embedding. Near real-time change detection, and this is based on TESSERA embedding. And so, but I'm not going to talk about details here because that will be another talk. But yeah.
Next time, yeah, sure. Yeah, we will invite you back. I think it will be very, very interesting to go back to Landsat. I think in my very like summarizing way of understanding Tessera, it's like a new way of analyzing this time series, compare a bit more length render, this algorithm developed by was Boston University. I don't remember the names of the university. Wait, let me say something wrong. But that was a quite powerful way of analyzing time series of Landsat before the hype of deep learning and foundational model. But yeah, and I think this is the next step. All right. Any other questions from the audience?
I've answered something like 20 or 30 questions, but I may have been somewhat rude and short just to get the answer out in time. Please do feel free to reach out to Frank or me by email. We'd be happy to answer more in case I didn't answer your question properly.
Wenbo, you have a question, yeah, or a remark?
Yeah, really. Thanks to Frank and Keshav for the wonderful presentation and of course the the work itself. And I'm thinking from the geo perspective, and so it is a pity I don't see kind of contributors or leads of the work program activities like GeoGlam work on crop monitoring, GeoTrees on forest monitoring. So they are not here, and wondering, if you are interested in kind of a get to know and potentially, collaborate, with teams who are working on a daily basis, to do the real work to map the forest, to map the crop.
I mean, from our perspective, we are very keen to work with anybody doing downstream tasks, but we've sort of are unable to have the compute all the time to participate in downstream tasks themselves. So what we've done is to create these embeddings, and then we collaborate with partners who want to use the embeddings. And as Frank mentioned, what we're doing is that we are making these embeddings available, and you can prioritize ones that say, okay, we'd like to have these done sooner. We're trying to do that. But beyond that, the paper, which is on archive, you can see how we did the downstream tasks for 5 or 6 downstream tasks. And hopefully that gives you a template for what you could do yourself. But we just don't have the capacity to do the downstream tasks. So we would be very happy to talk to these people and get them started.
Wonderful. So I will make the connection and see see how it works.
Great. I think then we thank you again for this very nice presentation and very interesting work that I think it's a really next step in this geospatial foundational models, and I think we are just starting, and there is so much probably to explore in the future. So thank you so much for be available and do this presentation for all of us, and also to all the people that attend. It was quite a bunch of people. We will reach almost 100 participants. So thank you everyone for attending the meeting, and see you next time for the new AI4EO GEO webinar. So thank you everyone. So let's do this virtual